Welcome to another great video. So today we are on atomic combinations, that chapter, but specifically I would like us to focus on these items that I've listed here. First, how chemical bonds are formed. Secondly, the potential energy versus that distance between the nuclei of atoms, that curve. Thirdly, the relationship between bond strength, bond length, molecular size, bond order, and electronegativity, right? And then lastly, I would like us to focus on a past paper example so that we can apply the knowledge we would have learned up until that point, right? So let us start here. You remember the structure of an electron, right? In an electron, there's a center. In that center, we call that center a nucleus. That's the center of the atom. So not an electron, the center of the atom. In an atom, there's a center. That center, we call it a nucleus. Right, so the nucleus is positively charged. Why? Because in the nucleus, remember, there is a mixture of, there are both protons and neutrons there. But since the neutrons are neutral, they have no charge whatsoever, if you think of it like that. So that means now the nucleus itself will have an overall net positive charge due to the presence of the protons in there. Right. So now this is the nucleus, and then around it, it is surrounded by a cloud of electrons. Let's draw it like this, right? So now this is our atom. In the center, it has a nucleus, which is positively charged, and then around the nucleus, it has a cloud of electrons. Let's put some negatives there to show our electrons. Okay, I won't fill the whole cloud with electrons. They're quite a lot, depending on, of course, the type of atom we're talking about. Right, so let's say this is our atom. Let's call this atom 1. This is our first atom 1, or atom A. Right, so what happens now if we bring another atom here next to this one? Let's call this atom 2. Right, we bring another atom next to this one, atom 2. Well, now the same thing happens, of course, to the second atom, because atoms are structured the same way. The center, they have a nucleus, and then around the nucleus there's a cloud of electrons, right? Negatively charged. So depending on how far these two are, depending on the distance between them, they will exert electrostatic forces. If you remember very well, we say the basic rule says like charges will repel, whereas unlike charges will attract. So which means a positive and a negative will attract, because those are unlike, and then a negative and a negative will repel, or a positive and a positive will repel as well, because those are like charges. They are the same charges. So the same interaction will be expected, or will happen, between these two atoms, right? You have these two centers. They are both positively charged, right? So if these are close enough to one another, these two centers, or the nuclei, right? The nuclei will exert a force of repulsion on one another. So you'll find that the nuclei of atom 1 exerts a force of repulsion on the nucleus of atom 2, such that, let's draw our force vector like this. This is the repulsive force exerted on atom 1 by atom 2. Then this is the repulsive force exerted on atom 2 by the nucleus of atom 1. Okay, so now we're just focusing on the nucleus. We can even write it. You can say force. This is an electrostatic force, by the way. We're talking about charges here. right? As you can see, I've labeled it electrostatic force of repulsion by atom 2 on atom 1. Okay, so by this atom on atom 1. All right, so the same thing would apply here. We're not saying that the force exerted by these nucleus will be necessarily equal, but we are saying that it will be a reactive force. It will be an right. Let's put this one as well. But now this is the electrostatic force of repulsion exerted by atom 1 on this atom, which is atom 2. All right, so you have something like this. This happens when we focus mainly on the nuclei of the atoms. Remember, one nucleus is just called a nucleus. Now if we have two nucleuses, they are called nuclei, right? So now if we bring the focus to the cloud of electrons surrounding these two atoms, let's say we focus on this one. This is my electron here. So this electron will exert a force of attraction on the nucleus of atom 2. So the electron of atom 1 will exert a force of attraction on the nucleus of atom 2. Why do you think that is? Well, because these are unlike charges. So between these two, there will happen to be an attractive force, right? So the same thing that happens is also going to happen on atom 2 to atom 1. So what I mean by that is the electron on atom 2 will exert a force of attraction on the nucleus of atom 1. Okay, so let's try and draw this. So what happens is, firstly, all the electrons in that cloud of atom 1 will want to exert a force of attraction on this. For now, don't focus on the length of my arrows. They are not representative of the magnitude of the forces exerted, right? But focus on the idea rather. So the electron cloud of atom 1 exerts forces of attraction on the nucleus of atom 2. Okay, same thing happens. The electron cloud of now atom, let me put another, the electron cloud of atom 2, we are focusing on one electron here because it's a bit strange to try and draw all these forces exerted by the entire electron cloud on that nucleus. But just imagine we are focusing on one point, right? So what we can say is the electron cloud on atom 2 will exert a force on the nucleus of atom 1. Okay? This is what happens. So now if we take a step back, just a step back and see what's happening here. There are two kinds of forces that are being exerted between these two, or being exchanged between these two atoms. It's the force of attraction and that of repulsion. Now, if you remember how force works, there will tend to be a net force that will summarize for us the overall interaction. So what I mean by that is, if you remember, when we have different force vectors, say we have some going like that, this was maybe F1, F2, and then you have other forces maybe going to the other direction. Usually we would draw them parallel, right? You would then find the resultant force, right? You would then find the resultant force. It's the same thing here with these two atoms. So what happens is there will be a resultant force that will happen here. So remember, when we're talking about attraction and repulsion, the resultant force can either be an attractive force or a repulsive force. So if we take the resultant force of these force interactions between these two atoms, and it happens that the net force that we find is repulsive, then there won't really be a bond formed amongst these or between these two atoms. But if it happens that that net force is an attractive net force, then a chemical bond will be formed between these two atoms. All right, so that's how it works. So we can even summarize this. So that brings us to our first definition, which is chemical bond. But before we get there, just to summarize, we're saying we have these two atoms, right? The nucleus of atom 1 exerts, the nuclei of each atom exerts a force of repulsion on one another, right? The nuclei exert force of repulsion on each other, right? That is the electrostatic force of repulsion by atom 2 on atom 1 and the electrostatic force of repulsion by atom 1 on atom 2. What happens on this side has to happen on that side as well, because it's a reaction pair, or it's an action reaction pair, right? So now what will happen as well is the electron cloud, like we've already said, the electron cloud of atom 1 will then exert an attractive force on the nucleus of atom 2. And then the same thing happens. The electron cloud of atom 2 will want to be attracted to the nucleus of atom 1. Right? Force of attraction between the electron cloud 1, which is from atom 1, of course, and then the nucleus 2, which is from atom 2. And then also another force of attraction between the electron cloud 2, which is from atom 2, and the nucleus 1, which is from atom 1. All right, so I just numbered them so that it's easy for us when we are discussing to be able to track which atom we're talking about. All right, so that's what will basically happen, okay? So now, like I said, if it happens that the net force is an attractive force, then a chemical bond is formed. So that's our third point. Right, and then lastly then, as I said, if the net force is an attraction force, then a chemical bond will be formed between atom 1 and atom 2. So that's pretty much what happens for a chemical bond to form. Now, there's also a bit of more things to discuss about after the bond is formed, or during the whole formation of the bond. What happens to the potential energies, or the overall potential energy of these two atoms, right? So, but before we get there, this is our summary for how a chemical bond is formed, okay? All right, so now we then get to define what a chemical bond is. Basically, every step I've outlined here is definition of what a chemical bond is, right? So we usually say a chemical bond it's a mutual attraction, right? So between two atoms, and then usually we say it resulting from that simultaneous attraction between their nuclear and then their outer electrons, or that electron cloud I've been talking about. So that's why I was saying every step I've outlined here pretty much is describing the chemical bond and what it is, right? And that's how we define our chemical bond. So it's the mutual attraction between two atoms resulting from the simultaneous attraction between their nuclear, as if you check those purple arrows that we drew here, their nuclear, the plus, and that minus in their outer electrons, sorry. So that's pretty much what happens for the formation of a chemical bond. All right, so now what I want to show you is once they have bonded, they are separated at a certain distance away from each other. So the way what we focus on to measure that distance is we check how far are their centers away from one another, relative to one another, right? So what that means is we just want to know, let's say I take this very same thing, right? I'll remove everything else. Right, so now once these two have formed a chemical bond, right, let's say they form a chemical bond and boom, there they are, right? Because remember, this force of attraction, that net force of attraction, will pull them as close as possible to one another. So even though they will be as close as possible, there will still exist a distance between their centers, or a distance between their nucleus, because remember, at the center of each atom we find a nucleus. So I'm pretty much saying the same thing. So we usually measure this distance from that nucleus to the other one. Let's use this distance. Okay, the distance between their nucleus. All right, so that small distance, it's called an internuclear distance, right? It just means the distance between the nucleus of atom 1 and that of atom 2, right? So we will talk about it on our next focus. This brings us actually to our next focus. But once these two atoms are in a chemical bond, they will exist that distance. Well, let's check how it affects everything. Okay, let's label it. So internuclear distance, this is how we write it, or the distance between the nuclei of the atoms. It's just an average distance, and then I will show you how it affects almost everything. So keep this idea in mind. Now let us start describing these whole steps, but now in what we call a potential versus the internuclear distance curve. Okay, so that's where the internuclear distance concept comes from. This one, internuclear distance. So we'll be talking about it in this curve. Potential energy versus that nuclear distance. All right, so let us sketch how the curve usually looks like. So now on the y-axis, this is where you would find that potential energy. And then on the x-axis is where you would find the internuclear distance. So the relationship is between these two parameters, right? Or these two variables. That's our 0 there. Okay, you can maybe make this some value 200 minus, because it's below 0, minus 400. This one maybe. This one we can make it 200. We're just labeling our graph, okay? Now, this is the y-axis of the graph. We call it our potential energy. is potential energy of these two atoms. So we're plotting that against the distance between the nucleus of one atom relative to the nucleus of the second atom. So this potential energy is measured in kilojoules per mole. Okay. And then on this side, internuclear distance. Well, it's measured in very small conventions. You'd find that it's in picometers or it's in micrometers or something like that. But it's a very, very small, because remember, these are atoms, so they're very tiny. So it's either in micrometers, nanometers, picometers, and so on, but very, very small numbers. All right, so here's how it works, okay? So we want to track, because that's what we're essentially doing. We are tracking this potential energy of these two atoms as they move toward each other to form the bond, okay? And after forming the bond, what happens if they keep moving close to one another, right? So now, all right, so when we start the curve, right, the atoms are pretty much far from one another. Let's put our plus there. Okay, not plus. Before they bond, they are far, far from one another. They start a bit far from one another. Not so far, obviously, but just imagine that they are far. Right, at that point, we are here at the start of our graph. Right, so what we are looking at is the potential energy of both of them in this system. Think of them as a system, right? So we are not looking at the potential energy of each individually, but of them as a unit or as a system, right? So when they are far from each other, the potential energy of that system is pretty much close to, if not zero, it is zero. Let's think about it as zero, right? So when it starts, the graph will be here. The potential energy is zero. So the graph is somewhere there, right? As they come closer, the potential energy keeps dropping, right? So why is it dropping? So as they come closer, the forces of attraction and repulsion now get affected. So both atoms now are exerting forces of attraction and repulsion on one another. So remember what I said, or what we said previously. We said if it happens that this net force is that of an attraction force, then these two atoms will form a chemical bond. So effectively what they're trying to do is they want to form this chemical bond, right? So as they approach that bond formation state, or that state where their potential energy will be at a stable value, right, the energy will be dropping meanwhile until they reach that point. So now we're starting here at zero. This is when they are far apart. Okay, I think I've made them too far apart. Let's just create a small distance. Yes, at this point they are a bit far apart. Okay, atoms are still far apart, and then they keep getting closer to one another. Let's say maybe somewhere here. In fact, we can use the very same ones. We can call this our stage 2. Right, they keep getting closer and closer. Right, here they are closer, there they are far apart. Okay, so there's this interaction between the attractive and the repulsive force between these two these two atoms. Now, as that happens, the potential energy keeps dropping. It keeps dropping, it keeps dropping. And remember what we said, this is just the potential energy of the system, not the individual potential energies of each atom. Okay, so it keeps dropping until it gets to a point where it is a minimum value. Let's see if I can get this to be a curve. Yes, something like this. So now it gets to a point here where now it is a minimum value. So at that point, it will reach that point when both atoms now have bonded, or whenever it reaches that point, this is where the formation of the chemical bond occurs, right? So remember, we're starting here. They are far from each other when we start. Atoms are far from one another. Right, they are far from each other. In other words, the internuclear distance is greater at this point. Remember, this curve is that of potential energy versus the internuclear distance. So when they are far from each other, we are saying the distance between their centers is larger at that point, or the internuclear distance is larger. All right, so now as they get closer to one another, this internuclear distance drops, because remember, let me just remind you of the basics. If I move from 0 in an x-axis and I go to the right, this is a positive x-axis, I am increasing in value. So you can just put values here, random values, so that you can conceptualize this. You can maybe put 5, 10, say this is 20, or 15. No, let's use 15. Maybe this is 20, 25, 30. Maybe this is 35. Okay, these are all picometers. All right, so if you check, as we move from 0 going to the right, the value of the internuclear distance is increasing. But as we move from right going back to the left along the same axis, which is the x-axis, the value of the internuclear distance is dropping. All right, so now this potential difference of the system of these two atoms combined keeps dropping until a certain value is reached. This value is the lowest possible value of potential energy that can be reached. And at that point, they will have formed a bond, a chemical bond. So a chemical bond will form at this state. So we take these very same atoms. Now at this point, they have reached a point now where chemical bond between them is formed. Okay, so now they have formed a chemical bond. Let's highlight that. All right, so the atoms have formed a chemical bond. And at this point, you see that our internuclear distance is lower than where we started, right? Because they are closer to each other now. So at this point where the chemical bond is formed, the potential energy as well would be at a minimum. So what happens is, the whole story with the potential energy, what these atoms are trying to do in essence is they want to reduce the potential energy to be so low such that they can form a stable state. So they are more stable when the potential energy is as low as possible, right? If the potential energy is high, the atoms become unstable. So that's why as they are approaching one another to form the bond, you find that the potential energy is dropping, right? As soon as the chemical bond is formed, we know that it means that the atoms have reached the state of the lowest possible potential energy. And at that state, they are very much stable. They are very, very stable. All right, so what also happens, or what it means as well, is that at that point, the forces of attraction and the force of repulsion, they are at equilibrium. All right, so at this state, let's label this state. So many things are happening here. Actually, let's label our graph state A, then this is perhaps state B. Okay, so at B, point B, we said force of attraction is equals to force of repulsion. We said the potential energy is at the lowest possible value. It's at a minimum value. We call it a minimum value. And then we say that these atoms have reached a stable state. They are very much stable now. All right, so that's what happens. And then if now they continue, and then let's say we try to force them close to one another again, what will happen is the energy, this potential energy, will start to rise now. It will start to rise. It will start to rise and so on. Right? If let's say we keep pushing them to be closer to one another for whatever reason, or if something else pushes them, right? So they will the potential energy will start increasing again. Okay, so it becomes a bit unstable, right? So that's what happens when we keep pushing them even further. So what we're saying is from point B to the left, okay, this is our point B. Our curves look, the curve looks funny. Let's try and make it. All right, this is much better. Now, so at point B, chemical bond is formed, minimum potential energy is reached, and the stable state is reached. These atoms are now in a bond. All right, so if we try, and if by whatever external force tries to bring them together again, to keep pushing them closer and closer and closer, what will end up happening is the potential energy will increase because they'll become unstable. The reason for that is now, remember, when they were at point B, the forces of attraction and repulsion were equal. Now that if you try to push them again closer to one another, the forces of repulsion will start dominating more than the forces of attraction. So it's like if you try to push unlike poles of a magnet together, they will try so hard to repel, right? So what that does, it builds potential energy. The potential energy will increase, right? The forces of repulsion are now dominating, right? So this state is a bit unstable. You don't need that. All right, but our main focus now is at point B. So at point B, we get a lot of things. We get the bond length, right? Because remember, the bond length, we only care about it once a chemical bond is formed. It is basically the distance between the nucleus of one atom to the other atom, or it's the internuclear distance at equilibrium or at point B where a bond has formed, right? So, and then another thing that we care about is the bond energy. I know I've introduced quite a few new concepts. Bond energy is this one. If I read from that point where the bond is formed to the y-axis where this way our potential energy is, I will get what we call a bond energy. So bond energy tells us that during the formation of this bond, how much energy was released. Why released? Because remember, we're moving from a point where these atoms were far from each other, and as they were drawing closer to one another, when the attractive forces were dominant and they were drawing closer to one another, what ended up happening is energy was being released throughout this whole process until point B. So at that point, how much energy have we released? We call this the bond energy. So this is the very energy that is needed to form this bond, but at the same time, it's the same energy that we need to break this bond. Okay, so we call that bond energy, right? We will define these terms in a minute. So, but now let's focus on our curve and finish telling a story on this. Right, so that's what happens. Okay, so what I want to show you is if you check, what this means is that from point B, from A to B, what's dominating there are the forces of attraction. Then from point B to whatever point, let's say maybe if there was a point C there, It's hard to label because the graph is increasing almost indefinitely. Right, so let's say from point B to C, there we have repulsive forces dominating now. So from point A to B, we have attraction forces dominating. Then from B to C, we have repulsive forces dominating. All right. So we can come and label our curve now. This is our bond energy. So now when we are asked to given a graph of potential energy versus the internuclear distance, and we are asked to sort of take out the bond energy from that graph, even though the value is negative, when you report the value, you put it as a positive number. So what I mean by that is this would be 400 kilojoules per mole. Okay, just one thing to note. All right, so not just minus 400. Okay, so now we have bond energy and then we have bond length. Okay, bond energy and bond length. So bond energy would be this value, right? That would be our bond energy, while bond length would be that value. That would be our bond length. Okay, so this is what will happen there. So at that point B, we are looking mostly for those values. These are the values that we would be just focused on for this graph. Okay, then the other stuff is pretty much just you telling the story that, okay, between points A and B, attractive forces were dominating there. That's why these atoms were moving closer to one another, because they're being attracted to one another. Now from points B to C, we see the potential energy rising, which means these things becoming a bit unstable. That's where repulsive forces are now dominating. So we can add that to our graphs and say, well, between A to B, right, attraction forces are dominating. Right, so we've added that at points A to B, attraction forces dominate, and then at points B to C, repulsion forces dominate. Now let's focus on point B before we move forward. So at point B, right, we will have that 1, the forces of attraction are equal to those of repulsion. Right, forces of attraction are equal to forces of repulsion. What else do we know about point B? At point B, potential energy is at a minimum. Is at minimum. What else do you know about point B? It's a stable state for these. Actually, we should write it here. Stable state. The most stable state that these two atoms can reach, right? That's point B. Now, another thing about point B, remember point B is a very important point in this graph. Point B, we find the bond length and the bond energy. And then, let's see, before we get to those ones, we find bond energy and bond length. We will define these terms officially in just a minute. So now we find point B, we find bond energy and bond length, right? These two, bond length, and we said bond energy, right? It's important. All right, so now what else happens at point B? Just to state the obvious, we must add that the chemical bond is formed at point B. Right, so those are all the things that happen at point B. So this is the most stable arrangement possible for these two atoms, since it takes the maximum amount of work or energy to pull them apart from this specific, let's call it a comfort zone, right? So from this specific state, it takes a lot of work or energy to pull them apart, right? So this is a stable chemical bond that is formed right here at the bottom of this curve. Okay, so that's the thing about point B. Now, just to state our definitions now, because we've introduced new keywords now. We've introduced bond energy, we've introduced bond length, right? And I did mention that bond energy, essentially what it means is the amount of energy that was released to form that bond, but also that amount of energy that was released is equal to the amount of energy that would be required to break the very same bond. And then bond length, I've been mentioning bond length as just this average internuclear distance between the two nuclei. All right, so bond length and bond energy. Let's introduce the official definitions. You would also find these on your study guides or your textbook, and also your exam guidelines. We have bond energy, and then we will also talk about the bond length. Well, we've spoken about it, but we're just defining them now so that you have those definitions. All right. Right, so bond energy, we say it's the energy required to break one mole of a molecule or compound into separate atoms. Right, 1 mole of that molecule or compound into separate atoms. That's why when we report potential energy, it's in kilograms per mole. It means how much energy would I need in the context, of course, of bond energy. How much energy would I need to break just 1 mole of that molecule? Okay, so that's one other thing. And then bond length. Bond length is the average distance between the nuclei of two bonded atoms, which is what I showed you here, this internuclear distance. All right, so that is what we call bond length. All right, so I think in fact I should have moved this to the, might be a bit bigger though. All right, should be fine now. So that is bond length. All right, then one last thing to state before we move forward is another thing that will happen for the bond to actually form is when it reaches point B, we will find that the potential energy of this system, which are these two atoms combined, will be less than the individual potential energies of the atoms. What that means is, let's say atom A or atom 1, say this is atom A, and then this is atom B, or atom 1 and atom 2. So when we look at them individually, you might find that maybe this one has about, let's say, 100 kilojoules per mole, and then this one has about, let's say, maybe, we're just making up values, okay, 80 for the sake of this example, 80 kilojoules per mole. So now for them to combine, when they finally reach that steady state or that stable state, which is when they reach point B and then they form the bond, what happens is the potential energy of the system now, you will find that it will be less than the individual potential energies of these two atoms. So you'll find that maybe it is a value of, say, 70. Okay, so when they are together, you find that they have a potential energy of 70, but individually you would find that they had a total potential energy of 180, right? Because A had 100 and B had 80. That's what we mean when we say at that stage, for the atoms to be able to form a bond, the potential energy of the atoms combined would be less than the sum of the individual potential energies of the atoms. Okay, so that's another thing that you must note. All right, so now that's what will happen. So let us continue. All right, so at this point we've talked about the chemical bond, why it forms, where it all starts, and then we've talked about bond energy, bond length. Now I want us to talk about the strength of a chemical bond, right? Strength of a chemical bond. So let's talk about that. Let's call it bond strength. So now the bond has been formed, right? And if you remember, we have different kinds of bonds. We have double bonds, triple bonds, single bonds. But I will show you how all of that matters now. So now, bond strength. Okay, so when it comes to bond strength, a few factors affect bond strength. So if you remember, at the start of our lesson, I listed them here. The length of the bond length, affects the bond strength. The molecule size affects the bond strength. The bond order affects the bond strength. And then electronegativity as well affects the bond strength. But these things are not, you don't look at them in isolation. They are actually not individual contributing factors to the bond strength. They are interchangeably in a relationship with one another, basically. So for instance, you will find that because of the size of a molecule, the bond length will be longer, right? And because the bond length is longer, you'll find that therefore the bond strength is a bit weaker, right? Or similarly, you might find that, okay, now the bond order, maybe when we talk about bond order, we're talking about, is it a single bond, is it a double bond, or is it a triple bond, right? So you might find that the triple bond has a lower bond length than the single bond, right? And therefore, because of that, the triple bond will have a higher bond strength than the single bond. You see, so the bond length, bond order, they are related in a sense. They are not, we don't look at them individually. Okay, so that's our next focus point now, bond strength. All right, so the factors that affect bond strength. Right, what are they? It's everything that I've listed here. We can just take these. These are all the factors that would likely affect your bond strength. You find that the bond length, the molecule size, the bond order, and electronegativity. Just briefly, so electronegativity, what it does is the difference, if that difference in electronegativity between these two atoms that are bonding to form a molecule or a compound, if the electronegativity difference is large, or the larger it is, what will tend to happen, or what it means physically, is that those two atoms will be pulled, will have a greater force of attraction to pull each other towards each other, to have higher attraction forces. So what that means is, if they are pulling so hard towards one another, the bond length will be at the lowest possible value, right? So the bond length will be as low as possible. And remember, the shorter the bond length, the stronger the bond strength, right? So that's another way in which the bond strength is affected. So let's look at all of these individually, right? So let's start with bond length. Now, when it comes to bond length, we will say the shorter the bond length, the stronger the bond. So for instance, if let's say we are comparing similar atoms, the one with a shorter, not similar atoms, similar molecules, the one with a shorter bond length will have a stronger bond compared to that other one with a longer bond length. Let's say molecule A has a bond length of 50 picometers, and then bond B has a bond length, molecule B has a bond length of 30 picometers. So the one that has the lower, which is 30 picometers, will have a stronger bond. Okay, so the shorter the bond length, the stronger the bond. Right. So then now on number 2, we look at molecule size. What we mean by molecule size is, okay, first let's look at how it affects the bond strength. A larger molecule, or if the atoms that make up a molecule, they are large, they will tend to be they will tend to have a higher bond length because they have a larger distance between their centers. I will show you that in a minute, what it looks like. So larger molecules tend to have higher bond length, and then because they have a higher bond length, what happens is this will affect their bond strength, because remember, the longer the bond length, the lower the bond strength. Lower bond strength. The opposite is also true. So I will list one, and then the opposite of that is also true, right? Bond strength. Right? So what does it look like? Imagine that same case where we have two atoms forming a molecule. Let's say this is molecule A. Molecule A all right, so finally my atom is allowing to draw. So now imagine we have something like this, right? These are two atoms of one molecule, and then they are bonded to one another, right? They are bonded nicely to one another. So now, if we measure the distance between their centers, you will find a specific value. This is the internuclear distance. This is the bond length, okay? You'll find a certain value. Now, I'm sure you can agree that this value that you'll find here, let's say this is molecule A. Molecule A is made up of atom 1 and atom 2. let's go to molecule B. So molecule B will be made up of atom 1 and atom 2, of course. So check these two molecules. Do you see the difference in size? These ones are smaller. Molecule B is smaller than molecule A. Now, if from here you can already see that if I were to measure the distance between their centers, it's a small distance compared to molecule A. Do you see that? It's very, very small. Right, so what that means, it allows this thing to have, it allows molecule B to have a shorter bond length, thereby forming a stronger bond. Okay, that's what we mean by molecule size. But then how do we see molecule size? If you go to your periodic table, right, just brought my periodic table now. If you go to periodic table, what do we mean by molecule size? So let's just focus on this group, for instance, group 1. So molecule size, we're basically talking about that value here at the bottom, which is what? The atomic mass, right? So the atomic mass will tell us how big that atom is. And then now when that atom forms a molecule, we will be able to find the overall atomic mass of that molecule. Okay, so we are talking about that atomic value. The bigger the atoms, you know that obviously if I have two big atoms, they will likely have a lower they will likely have a lower bond length, bond strength than if I have two smaller atoms. So what does that mean? Let's say, for instance, I have a hydrogen gas compound like this, a hydrogen gas molecule, sorry, like that. And then now what happens is if I compare it with something like maybe sodium hydroxide, this is a bigger molecule than hydrogen, right? It's a bigger compound than hydrogen, right? So now when I find the mass or the molar mass of sodium hydroxide, I'm sure we can agree that it will be way larger than that of hydrogen. For hydrogen, you'll find something like 2, right? And then if you go and find sodium hydroxide, already sodium by itself contributes about 23 grams per mole. And then the other ones, hydrogen is 1, oxygen is 16, right? So that's 23 plus 1 plus 16. That's way, way, way bigger than 2 grams per mole, which is that of hydrogen. So already that molecule there will have, most likely will have a weaker bond than hydrogen, right? Or even if it doesn't have a weaker bond, it will have a larger bond length than hydrogen. Okay, so that's one thing that we mean by molecule size and how it affects bond length and thereby affecting bond strength. Okay, usually though, for us to compare such things when we use molecule size, it's usually molecules that are similar. It's molecules where it's halogen bonding maybe to a similar atom, thereby forming a similar molecule, right? So you don't compare non-similar molecules when you're looking at molecule size, right? Because if there's a confluence of factors there. But moral of the story, just know that the larger the molecule, the higher the bond length, therefore the lower the bond strength. Okay, so by molecule size, we are referring to these atomic mass numbers. All right, so I think for the purpose of this, we can just say, let's check group 1. Group 1, we know that these values will show us atomic mass. Right? And we know that if this atom was to bond with another atom and then we check this mass, if it's greater for molecule A compared to molecule B, then we know that the bond length will be greater for molecule A, right? So that's what we mean by molecule size. Okay, this is consuming a lot of space. I don't think I'll include. Let me remove this. Now, I think this diagram on its own is enough. Then I can say we usually look at molar mass or the atomic mass. All right, so now let's go to our third point, which is bond order. Then just to the opposite is also true. Right, remember we said the opposite of larger molecules is smaller molecules. Opposite of higher bond length is lower bond length. So what I mean is the smaller the molecule, the lower the bond length and the higher the bond strength. The larger the molecule, the higher the bond length and the lower the bond strength. All right, so bond order refers to whether a bond is a single, double, or triple bonds. Which one is it? Right. So remember, when it's a single bond, you'll just have molecule X maybe bonding like this, and then there's one line in between. Usually for a double bond, it's molecule X and not molecule, sorry, atom X and atom X again, or atom A and atom B. And then these double lines show us that that's a double bond. And usually a triple bond, you have three lines like this. So we will focus on these bonds on our another video. You can check that out. We are doing the Lewis dot diagram, and then there you will find how we find all these triple bonds. But for this video, our main focus is just on how it affects the bond strength. Okay, so bond order, how does it affect bond strength? Usually a higher bond order will have all right, so let's talk about bond order now. So while on bond order, so like I've said, we have a bond order simply means this, is it a single, is it a double, or is it a triple bond, right? So it's either atom A to B, they are separated by a single bond, B, A to B, or separated by a double bond, or A to B separated by three lines, which is representative of a triple bond, right? So, but and how does it affect the bond strength? So typically what tends to happen is, usually the stronger the bond, the more energy you need to separate the atoms that made that molecule. So okay, let's do this. All right, so usually what happens is that the stronger the bond, the more energy needed to separate the atoms that made up that bond, or the more energy needed to break that bond, right? So the higher the bond order, the stronger the bond, therefore the more energy needed to break that bond. Alternatively, the higher the bond order, the stronger the bond, and then the shorter the bond length. So let's write it here. Higher bond order means that bond is likely stronger than a lower bond order, right? The shorter the bond length, and therefore the higher the bond strength. Okay, let me remove the higher bond strength. Think about it. So if the bond is strong because it's a high bond order, what happens is, oh, I missed, there should be something here saying the stronger the bond. All right. So what happens is, oh, it's there. What happens is, if you think about it, when you have more atoms being shared, they create a higher bond order, right? Because remember, what we are discussing thus far, these are all covalent bonds from the start of the lesson, in case I didn't make it clear, right? This chemical bond formation here that we are seeing, it's covalent bonds from the start when I was talking about the atoms to potential energy until at this point. We are just talking about covalent bonds, right? So now what happens is, the higher the bond order, that means that bond is pulling those two atoms that make up a molecule closer to one another. It's this, the pull is so strong, right? What tends to happen then is it will result in a shorter bond length because they are pulling towards each other at a higher force of attraction, right? So now what tends to happen as well is, that means since the bond length is shorter, the bond strength will be higher. So that's what we talk about when we talk about bond order. So remember that it's like that famous adage that says we are stronger together than when we are individually, right? We are stronger together as when we are united than when we are separated, or than when you are by yourself. Think of that, and that's typically what happens with bond order. When this is just a single bond, yes, the bond will be strong depending on other factors, but when we're just talking about bond order alone, it will be weaker compared to a higher bond or a higher bond order, which would be a triple bond. So in essence, a triple bond will always be stronger than a single bond, right? Or would mostly be stronger than a single bond, right? So now that's what happens when it comes to how it affects the bond strength. So remember, everything we're discussing now goes back to bond strength. All right. So what about electronegativity now? Electronegativity. Remember, with electronegativity, we said, okay, this is our fourth point. We said here we will be focusing on the difference in the electronegativity between the molecules. Between the atoms that make up that molecule. Electronegativity. All right, so in the case of electronegativity, what we talk about here is when these molecules, when the individual atoms that make up that molecule, when those two atoms have a very big or a very large difference in electronegativity, what tends to happen is they will exert a higher attraction force, and then they will be attracted to one another. They will pull each other so closely such that they will achieve a very short distance between their nucleus, which is the bond length, right? So as they do that, the bond length becomes shorter, and therefore the bond strength the strength of the bond will be higher. So the opposite is also true. For all of these items, or for all of these factors that we've been talking about, bond length, the opposite of what I said here, which is the shorter bond length, the stronger the bond. The opposite of that is true. The opposite of this one is also true. Larger molecules and so on. And then same thing here. The opposite is true. The lower the bond order, the longer the bond length usually. And then the higher the bond strength. Right. They may not come in this order, but they affect each other in this way. All right. So now, electronegativity, as I was saying, a large electronegativity difference between the atoms that make up that molecule or that compound or a high, let's use high. Electronegativity difference right? It means those two atoms will move so close together, making the bond length shorter. Those two atoms will move so close together, making the bond shorter. I'll write the other one in brackets. Shorter bond length. And thereby having a stronger I should have done this before that. Actually, I forgot to mention the stronger force of attraction. Let's put this here for now. So a strong force of attraction is usually attributed as well to a higher electronegativity difference between those two atoms, okay? So what then tends to happen is the stronger the force of attraction, the shorter the bond length, right? And therefore, these atoms will move closer to one another. And as they move closer to one another, let's do this. The bond strength will be higher. All right. Higher bond strength. So that's stronger bond means higher bond strength. All right, so these are all the factors that would likely affect your bond strength for a particular molecule where the atoms that make up that molecule are covalently bonded to each other. All right, so I think we've discussed them enough. All right, so we are pretty much done with the bond strength. So just in summary, bond length, the shorter the bond, the stronger the bond. Then when it comes to molecule size, what we are in fact talking about is how big is the molecule in terms of its molar mass. But the main thing that we are referring to there is the size of the atoms that are actually combining to form that molecule, right? So the larger those atoms as well, which obviously means a larger molecule, they will not be able to move close enough to one another, and then they will usually have a higher bond length because of that, and as a result their bond strength will likely be lower. While for if atoms are the size of those atoms that are combining to form molecule B in this case, if those atoms are small, what will happen is they are able to move closer to one another, as you can see with this distance here, right? And as they move close to one another, they will have a smaller bond length compared to molecule A, and as a result, so here I think in fact, let's say as a result molecule B will have a higher bond strength than molecule A. So here I think, let's say, how big are, or size in a molecule. And then I can say I was referring to the molar mass. Okay, yes, I think this is much more clearer. Right, so, and then bond order, single, double, or triple bonds. It refers to that. That's what bond order means. And then the higher the bond order, usually it is attributed to higher bond strength and therefore a shorter bond length, right? And then we said electronegativity. Usually when there's a strong force of attraction between atoms, it's because they have a high electronegativity difference, and the higher the electronegativity difference, it will cause these atoms to have a stronger force of attraction between one another, and they will pull towards each other closer when forming a bond. And therefore when they form that bond, eventually they will be so close to one another that their bond length will be as minimal as possible, and as a result they usually have a shorter bond length and therefore a stronger bond or a higher bond strength. Okay, so that's what we've done so far, and because of that we are done with the notes part of this video. Now let's do an example to see how we can apply this knowledge. And then just a side note, remember that if a bond is stronger, we need more energy to break that bond. All right, so the stronger the bond, the higher the energy needed to break that bond. Remember, that energy, we usually call it the bond energy. The higher the energy needed to break a stronger bond, okay? And then usually stronger bonds, they are also attributed to being more stable and not as reactive, or not as easy to break as weaker bonds. So that's one thing we need to note as well. But pretty much everything we've talked about covers those two. I was just clarifying there. Now let's look at the past paper example for this part of, we'll be just looking at a past paper example. All right, so we have this past paper problem from a Limpopo paper. I think it was 2025. So in this problem, we are told that we have a graph. If you check this graph, it's what we just did, a potential energy graph versus the distance between nuclei. So in this case, they just said distance between nuclei, and we called it the internuclear distance, right? So it's the same thing. And then, so it shows the energy change that takes place when an oxygen atom approaches a carbon atom during the formation of a carbon-oxygen bond, okay? Carbon to oxygen bond. So if you check here, this is a double bond. The bond order there is double bond. All right, so remember what we said. Whenever they are here, the potential energy is close to naught or close to zero, because they are far from each other actually. And then as they get closer to one another, it keeps dropping. Get closer to one another, it keeps dropping until this point where the bond actually occurs, at this very point, right? And at that point, we can take out the bond length and the bond energy. So our bond energy here is that, and our bond length is there. So bond energy would be that, and then our bond length would be that one somewhere there. Right, unfortunately there's a watermark to this paper, but I hope you can see the graph and the values and so on. Right, I'm not sure why it has a watermark. So now, define the term bond length is our first question. We've already defined what bond length is, so I'll just go ahead and take that. Where is our bond length here? In this lesson, we've already defined what bond length is. So remember, what I always say is, before you go to your exam, you make sure that all your definitions, you know them, right? Whether you have to memorize them the day before or 2 days before, whichever one works for you, but all your definitions, you know them, because they count for about 13% of that 150 marks. All right, so that's our bond length. It's the average distance between the nuclei of two bonded atoms. Remember, we are talking about covalently bonded atoms here. 4.2. 4.2, from the graph, write down the bond length in picometers, okay, of the carbon-oxygen bond. Remember, we said bond length, we'll find it here at the lowest possible energy. That's point E, right? So if we check, let's see how these lines are going. We have 240, 480, 720, 960. All right, so these things, they are in doubles. They are separated by 120 if you check. So what I mean by that is 240, 480. 480 is just twice 240. So that means this line in between has to be either 240 or 120. Let's see. Yes, so it would mean that if I were to include this line, I would have something like 360, because that's 120. And then if you add 120 to 360, you get 480. Then 480 to this line would be 480 plus 120, that's 600. And then you add another 120 to get to the next line, that would be 720, and so on and so forth. That means this one has to be 120. All right, so that's how you would find those middle lines. It's as easy as that. You just check what's the difference between, what's the scale that they are using, so the difference between these values as you move along the axis, right? And then you will eventually find that we usually use the same difference. You don't change it, otherwise there's no need for that. It's weird. Now 4.2.1, we are asked to find bond length in picometers. So our bond length is simply 120 picometers. That's our bond length, 120 picometers. PM, not PM for time, but picometers. Remember, pico is times 1 times 10 to the power minus 12. Then there's 4.2.2. 4.2.2 bond energy in kilojoules per mole needed to break this carbon to oxygen bond. Remember what we said at point E? That's where the energy that was released to form the bond is found. And at the same time, we know that that very same energy is what we would need to break this bond. So this is the 800. It's found at the lowest possible point of the curve. And we said we report it as a positive value, not that negative. The negative is just because we have an axis, and then below the x-axis, the y is negative. So that's why it's in negative numbers. But when we report it, we write it as a positive number. So that is 800 kilojoules per mole, right? And then we go to 4.2.3. Name the potential energy represented by E. We said that is simply the bond energy. So they are asking you to take this and put it there. Right, so now let's go to 4.3. How will the bond length of an SO bond, which is sulfur to oxygen bond, compare to that one of the carbon to oxygen bond? So they're asking us how will the bond length be? All right. And then write down equal to, shorter than, or longer than. Give a reason for your answer. So for this one, remember, there's a number of things that affect the bond length. Now, since they are both bonding to the same atom, sulfur and carbon, so what we can do is we can check how big is the sulfur atom and how big is the carbon atom. Let's go and check our periodic table, right? And then from there, we can say, well, if we check molecule size wise, what's the comparison? Okay, that's one thing we can check. We can't use bond order because they are both double bond, and electronegativity we can use as well, but our first focus for now, let's use molecule size. Where is it? All right, so let's check our periodic table. Right, we are looking for sulfur and carbon. So we know that carbon has 12 as a molar mass, or the atomic mass, and then sulfur has 32. All right, so we already see that sulfur is a bigger atom compared to carbon. So by virtue of molecule size, we know that the carbon to oxygen bond will have a lower bond length compared to the sulfur to oxygen bond. Okay, so we can just, if I were to draw it, it would be a similar situation to this one, but now let's draw it. They are both bonding to oxygen, right? We can imagine something like this. Compared to oxygen, sulfur is a bit bigger. Say this is oxygen, this is sulfur, and we'll use the same size for oxygen. But compared to sulfur, carbon is a bit smaller, but it's still bigger than oxygen. Do you see the difference? So now you will have something similar to something like this. So this is a carbon to oxygen bond. Of course, this is not the full molecule because it has to be carbon dioxide, but we are focusing on just one side of it. All right, so if you check, you might find that because sulfur, if we compare the distances, we would find that sulfur to oxygen has a larger distance than carbon to oxygen. So because of that, the molecule size of the sulfur to oxygen bond and the molecule size of the carbon to oxygen bond, you'll find that for sulfur to oxygen, the molecule size is larger, and then for carbon to oxygen, the molecule size is a bit smaller compared to sulfur to oxygen. Right, so for that reason, what was the question? Sulfur to oxygen bond will have a longer than, let's start there, longer than. Why? Sulfur is a bigger atom than oxygen, or it has a bigger atomic mass compared to oxygen. All right, that's one thing. Oh no, not oxygen, sorry, we are comparing it to carbon because oxygen is just one atom that they are both bonding to. So since sulfur is a bigger atom than carbon, the bond length will be longer for between the S. Let's just write the whole thing. Longer than S is a bigger atom than C. Therefore, the S bond will be longer than right. So just to add here, I think we said the atomic mass. I think we should write it here. For sulfur, we got that the atomic mass was 32. And then for carbon, the atomic mass is simply 12. Right. So you can see that sulfur is nearly 3 times as large as carbon. So that's why. Right. So that's our reason. And then let's go to 4.4. All right, so before we go to 4.4, I forgot to mention the electronegativity. In this case, we can't really use the electronegativity to compare these two. Why? Because the relative or the difference in electronegativity is the same, right? So if you take the difference in electronegativity between sulfur and oxygen, you'll find the same value if you did the same for carbon and oxygen. So we can't use that. And then same reason we couldn't use the reason of bond order, because they both have a bond order of a double bond. Okay, so that's why we can't use electronegativity. So the only thing that's left to compare is how large are these molecules. All right, so now we can move to 4.4. What can be said about the forces between the two atoms at point D? right? So remember, at point D, we said these things are so far from each other that their forces are either weak or they are not there. The attraction or repulsive forces at point D, they are weak because these two atoms are far from each other. Forces, let's use both attractive or repulsion forces. You can either say they are zero or they are weak. Atoms are far from one another. That's why they are weak, right? So that's what happens. And then let's just say since atoms are far from one another, the attraction or repulsion forces at point D are weak. That's your 2 marks right there. Then let's go to 4.5.1. 4.5.1. Describe the relationship between bond length and bond energy as shown in the table above. Okay, let's check it. Bond length, bond energy. So if you check, I'm not sure if you can see these numbers, but here we have 154 picometer, 134 picometer, and 120 picometers. So these are all bond lengths. And then here we have 348 kilograms per mole, kilojoules per mole, 614, and 839 kilojoules per mole. Now, so if you check, as I move from the single bond to the, I think this was supposed to be a triple bond. I'm not sure what they did there. So as I move from the single bond, as I move from A to C, my bond length is decreasing, but my bond order is increasing. And at the same time, as we move from A to C, the bond energy, is this the bond energy? Yes, the bond energy is increasing. So now the relationship between the bond length and the bond energy, now we can say as the bond length decreases, the bond energy is increasing. That's it. All right. Or you can say the shorter the bond length, the higher the bond energy. Or the other way around. The longer the bond length, the lower the bond energy. All right. Or we say it's decreasing. Right. So as bond length decreases, the bond energy increases. So this is a fairly straightforward example. And then let's go to 4.5.2. In the other videos, we will cover more of these past paper examples, and then you should be good enough to answer such questions in your exams. Now, which one of the bonds, A, B, or C, will be weakest? Explain. So remember, the weaker the bond, the lower the energy needed to break that bond. So obviously the weakest bond here is A. Why? Because it has the lowest bond energy. That's it, right? So your answer here would be A is the weakest. Why is it the weakest? Because it has the least amount of energy needed to break its bonds. And it's also a single bond, right? So we can talk about bond order and also the fact that it has the lowest bond energy. compared to B and C. Therefore, we will say less energy will be needed to break this bond. But it does sound like I'm saying the same thing here, because if I say less energy will be needed to break bond A, it's the same as saying bond A has the lowest bond, or no, bond A has the lowest bond energy. Here there's a low bond energy compared to B and C. All right, but it's fine. It's still correct, right? So A will be the weakest because it has the lowest bond order and a lower bond energy compared to B and C, right? Therefore, less energy will be needed to break bond A compared to the other ones. So that's how you would attack, or that's how you would approach a question like this, right? So here we would say S is greater than C. Right, so that's how you would attack a question like this. And thank you very much for watching. I will catch you again on our next video. Cheers.